Welcome to lesson 6. In this lesson we are going to explore some of the commands that you see on the screen. So let's start. First of all, we are going to convert our spanning tree topology to rapid spanning tree topology. For this we log into each our switch, CLI mod, say configure terminal, spanning tree, then we say mode, then we say rapid -pvst, then we say enter. It says warning, changing STP mode can disrupt the traffic and make system unstable. Recommend to change STP mode only during maintenance window. It's okay. Let's copy the command. Let's write it to the memory. Let's open switch 2 and do the same. Enable, configure terminal, paste, do write. Next, switch 3. Enable, configure terminal, and paste, do write. Then we go for switch 4. Enable, configure terminal, right click paste, do write. Then we go to switch 5. Enable, configure terminal, and paste, and do write. So all our STP topology should be converted to the RSTP. Let's check. We'll go to switch 1. We say exit and say do show SP. And as you can see, the switch shows for the VLAN 1, the spanning tree enabled protocol is RSTP. It says that this bridge is root, and the cost for the interfaces are the same. So nothing new, just we are back to our rapid spanning tree. Let's go to switch 2. We say exit, show SP, and we see that the root bridge is this one, 2000, which is switch 1, and the current spanning tree is RSTP, and the port costs are 100. Okay, then we go to switch 3, exit, and say show spanning tree. Spanning tree can see the root bridge, and it can see that the current enabled protocol is RSTP. Then we go for switch 4. Say exit, say show spanning tree. We can see that it can see the root, and the root cost is 200 because it's 100 to switch 2 and 100 to switch 1, totally makes 200. The spanning tree enabled protocol is RSTP, fine. Let's go next, switch 5. Switch 5, we say exit, show spanning tree, and we see that it can also see the root. Root is also 200, just from the different path, like switch 3 and switch 1. And the spanning tree enabled protocol is RSTP. We can see that the roles of the ports are same. It's root, alternate, designated, alternate, and the status are forwarding, blocking, forwarding, blocking. So as you can see, the CISCO implementation on the status is still blocking. It doesn't say discarding. So it's a CISCO specific status, which is same in STP and the same in RSTP, so that you don't confuse that you are still in the STP. No, you are not. You are in RSTP mode. Even though you have a role alternate and the status blocking, The blocking name comes from the IEEE of STP. Cisco is using also blocking instead of discarding for RSTP. If you have noticed that the topology is still same, nothing has changed. So the ports which were discarding or alternating or blocking are still the same. For example, let's go to the switch 3. Switch 3, it has also alternating blocking port 1/3, which is this one, 1/3, so nothing new. Then we can ask what has changed, and let's check the convergence time. For example, in previous lab test with STP, we were checking, and we have noticed that the convergence time for this PC was around 30 seconds, and convergence time for this port or any blocking ports on the switch were around 30 seconds. Now let's check if the convergence is still same. We go to again to switch 4 and we go to configure terminal. We can see that switch 4 has all ports designated and one of them is root, which is E0/0. And we can say interface E0/0. We can say shutdown. Then we can say do show spanning tree. As you can see, the port 1.3 immediately changed to the blocking and port 1.2 is changed to the forwarding. So 1.3 is this one, it's become blocking or discarding, and 1.2 became root. So it became root immediately. Then we can see that the other ports are in the learning state or in the designated, and the status is learning state. The port that we see is E0/3. This one is still in the learning state, and it stays like this for around 15 seconds. Why? Because the switch doesn't know if there are any other switch connected to this port and waits in the learning state to hear any BPDUs, and if it doesn't hear, it should translate this port to the forwarding state. So as you can see now, the E0/3 is in the forwarding state. Even with RSTP, we see that the PC connected to the switch during the topology change will lose its communication minimum for 15 seconds. Is there a workaround to reduce this time to 1 second or less? Yes, there is, and we will explore it in further sections of our lessons. So let's switch the interface back by saying no shut and see what is going on. We can see that the switch immediately changed the E0/0 to the root and forwarding state, and all other ports in the blocking state, but designated role. Let's check again. We see that all other ports are in the learning state. So only this port is working. All other are learning MAC addresses, learning BPDUs. And if we check again, we can see that they now shifted to the forwarding state. So it took around 15 seconds for the switch to switch to the forwarding state on all non-root ports. Let's imagine that we have a situation where we have a switch, let's say up to 48 Ethernet ports, and all of them are connected with the PCs or servers. So if there is a topology change, we will see an outage of up to 15 seconds. Is there a way to avoid it? In Cisco, there is a solution for this to specify the ports where the bridges or switches are not connected as port fast. So the port fast are the ports which have a server without any, let's say, VLANs or bridges, or it has a regular PCs which don't have any switch on the way. So in this case, these kind of technologies will not have a switching mechanism inside, like a bridge, and will not have a mechanism which is sending bridge protocol data units or BPTUs. In this case, we can tell the switch that it is safe to convert this port to the forwarding state immediately. So let's check. Let's say exit. Let's say spanning tree. And let's say port fast. But we are on the wrong port, so let's exit from here. Let's say interface E0/3, which is this computer. Spanning tree, port fast. We can say disable port fast, we can say trunk, enable port fast on the interface, even in trunk mode. No, we don't want this. We just want it to be enabled when it is in the edge mode or when only the computer is connected to it. It can be computer, maybe IP camera, maybe some IP phone. And we click enter. It says warning, port fast should only be enabled on ports connected to a single host, connecting hubs, concentrators, switches, bridges, etc. to this interface. When port fast is enabled, can cause temporary bridging loops. Used with caution. Then it says port fast has been configured on Ethernet 0/3, but will only have effect when the interface in a non-trunking mode. What does it mean? If you convert this interface E/0 to a trunk, it will disable the port fast. We are fine with that. We say do write, save the configuration. Let's exit, and let's check the configuration, show run for the E/0. You see here, it says interface Ethernet E/0 spanning tree port fast. So now let's check if the port fast will make any effect for the topology convergence speed. We say again configure terminal. We say interface E0/0. Then we say shut down. So we are shutting down this trunk port again. Then we say do show spanning tree. And as you can see, the port which is E0/3 is immediately in the forwarding state, and the other ports are in the blocking state. Then they will shift to the learning state. And as you can see, we have one more text here. It says edge. Edge means only computer is connected to it. There is no any bridge or switch. Let's go next. And you can see the other ports are still in the learning state. Other ports in the topology which are in the learning state are actually ports which are not visible in the topology. They are in the learning state. And topology convergence already happened. As you can see now, even invisible ports are in the designated and forwarding state. So as you can see, the convergence of the edge ports or spanning tree port fast ports, like here, is immediately, so that the computer doesn't lose its communication with the server or with whatever system it was having communication. Even if it loses, the duration is no more than 1 second. So let's go and switch back the Ethernet 0/0 on and see what is going on. As you can see, the interface 0/3 is immediately in the forwarding state. The Ethernet 00 is root, also immediately in the forwarding state, and the other ports are deciding what to do, like Ethernet 1/2, 1/3. They're still in the blocking state. Now they will decide. It takes around 15 seconds. And they are back in the forwarding state. So the port fast feature enables edge devices to converge immediately. Next, what we are going to do, we are going to check what kind of effect will make the interface speed or the bandwidth on the convergence and on the spanning tree topology. For example, as you can see here, all of the interfaces are by default on the CISCO switches in the EVNG have a speed of 10 megabit per second. Let's check it. Let's check it, for example, on switch 2. Switch 2. We say enable. We say show interfaces Ethernet, for example, 1/3. As you can see, we can see the statistics of the interface. It is up, line protocol is up, it is connected. The hardware Ethernet address is AABBCC00.3031. M2 is 1500. Bandwidth is 10,000 kilobit per second, which is 10 megabit per second. Then we see that the full duplex auto speed media type is from 10 to 100 to 1000. It automatically detects the duplex modes for the speeds of 10 megabit, 100 megabit, 10,000 megabit per second. Then we can see some statistics for the packets, and that's all. It's very interesting that we don't see the duplex mode configuration, or actually we see it. It is here. It says full duplex auto speed. So it has negotiated full duplex, but the full duplex is set not manually, but it was automatically negotiated. Okay, let's go next. So if we go to spanning tree, show spanning tree, we can see that the spanning tree costs for the switch 2 are below. Like each port that the switch 2 has a cost of 100. You can see that the root is on Ethernet 0/0, which is this one. And the rest ports are the designated ports. Let's check the situation for switch 3. We say enable, show spanning tree. And here we can also see that the root port is E0/2, which is this one. The rest ports are designated, and port Ethernet 1/3 is alternating discarding. Why? Because this switch has a higher bridge ID. Where is the bridge ID here? It's here. The bridge ID is 4000 and this one is 3000. That's why this port becomes blocking or discarding. But imagine, what if we have not a computer here, but a mail server. As you can see, I have changed the label of this computer as a mail server. If you analyze the topology, the spanning tree works toward the internet from here like this, like switch 4, switch 2, switch 1, then the router. From here it goes switch 5, switch 3, switch 1, and the router. And if you analyze the spanning tree topology, you can see that for this switch, the path to the mail server is suboptimal. What does it mean? It means that for the clients, let's say, which are connected to switch 2, to reach the mail server, they have to go first to switch 1 and then to switch 3. Is there any solution to make the switch 1 go to switch 3 and then directly reach the mail server and vice versa? Yes, there is a solution to increase the throughput capacity of the link. Currently, all the links are 10 megabits per second, but as you can see here, I have specified two links like this one, 1 gigabit per second and 1 gigabit per second planned. So what we can do, we can connect the cable between these two switches to something with a higher speed, let's say 1 gigabit per second instead of 10 gigabit per second. So the topology will change, like the root switch traffic will go from switch 2 to switch 3. Then if it needs to go to the internet, it will go to the switch 1 and to the router. If it needs to go just to the mail server or let's say to some FTP server, it will follow this way or this way. So how can we accomplish it in EVNG? In EVNG, we have only one type of cable and it is virtual. So basically in EVNG we can go to the switch configuration of the interface and change its bandwidth to, let's say, from 10 megabits per second to 1000 megabits per second or 1 gigabit per second. And we have to change it on both sides, on switch 2 and switch 3, Ethernet interface 1/3. After we change it, we will still have 10 megabit speed here, so it will not be enough just changing this part. We should also change this part so that the total cost to the root will be less than the total cost to the root with direct connection from switch 2 to switch 1. Why? Because the algorithm of the decision for the best path is the lowest bridge ID. Switch 1 says I am the lowest bridge ID. Switch 3 says yes, I can also have a connectivity to him, but my cost is higher. That's why switch 2 chooses switch 1. But what if switch 3 says my cost is lower, which is the second decision item, lower root path cost? Why and how it can be lower? For example, as you have seen, currently the cost of each interface is 100. And the total cost to reach for switch 2 to switch 1 is 100. And if it goes this way, it will be 200. What if we change the interface to 1 gigabit per second? We will have a cost from switch 2 to switch 3 as 4, but again from switch 3 to switch 1 as 100, and the total cost will be 104, so the switch 2 will still go through the switch 1 to the internet and to the mail server. That's why we have to change this path also, E0/2. In this case, this path will be 4 and this path will be 4, so totally the path cost will be 8. And 8 compared to 100 is much smaller. That's why the switch 2 will converge and select the switch 3 as the main root port. Also, if we change the speed not to gigabit but to 100 megabit per second, we will have each link cost of 19. If we change it to 10 gigabit per second, we will have it as 2. But in our lab, we are going to make it 1 gigabit per second. So let's start. Okay, now we shifted to switch 2 and let's change the bandwidth of, let's see the show spanning tree first. We see that the switch Ethernet 1/3 has a cost of 100 and we are going to change it to gigabit per second. Let's say configure terminal, interface E1/3, bandwidth, and the options are from 1 to 2 billions or 200 millions, I think. Yeah, 200 millions. We will say 1,000 thousands or 1 million, which is equivalent on 1 gigabit per second. Then we say do write. Then we say exit, then we say do show spanning tree. As you can see, the Ethernet cost of 1/3 is 4. It is designated port, it's not root port. Root is still Ethernet 1/0. So let's see from the other side, what about switch 3? Switch 3, let's go to the interface E1/3. And we say bandwidth. And we say 1 million. Say do write. Then we say do show spanning tree. And as you can see, the Ethernet interface 1/3 has a cost of 4, but it's still in the blocking state, alternate blocking or alternate discarding. Why? Because the total root cost still from switch 2 to switch 1 from this path is 104, but from switch 2 to switch 1 via this way is still 100. So what we have to do, we have to change the link cost of switch 3 Ethernet 0/2. we say interface Ethernet 0/2 bandwidth 1 million. Do write and say do show spanning tree again. As you can see, the Ethernet cost of 0/2 has been changed to 4. So this port is 4 and this port is 4 now. And as you can see, the Ethernet 1/3 has shifted from blocking state to designated state. Let's see if there are any changes here for the root. Yes, there are. The root port now has been shifted to 1/3, this one, instead of 0/1. And 0/1 becomes blocking. Why? Because Ethernet 0/1 has a cost of 100, but Ethernet 1/3 has a cost of 4. Let's change also for the consistency the Ethernet 0/2 bandwidth on switch 1. Let's say switch 1. Enable. Configure terminal. Interface E0/2 bandwidth 1 million. Do write. Let's say do show spanning tree. And for the switch 1, the root condition wasn't changed, just the Ethernet 0/1 has a designated port with the cost of 4. Let's see if there are any changes here. There are no changes. Let's see if there are any changes here. There are no changes. As you can see, the Ethernet 1/3 shows the root cost of 4. Actually, it should show the root cost of 8, but not 4. Why? Because here we see that the root cost is 4 here, and 4 plus 4 should make 8. Somehow the system displays it different way. Let's see what sees the switch 4. Enable show spanning tree. Switch 4 sees the root as Ethernet 0/0 with the cost of actually, we are looking on the wrong location for the root cost. Root cost is being displayed here. So the total root cost is 108, which is 100 here, then 4 and 4 more. So let's go back to the switch 2. We can see that the root cost is shown here. It's 8. So 4 plus 4 is 8. So the switch 2 shows correctly root cost here, and here is only displayed the interface cost. Let's go to switch 1, and the switch 1 says, no, switch 3, and the switch 3 says that the root cost is 4. Why? Because it has only one link. And the interface cost is 4, it's fine. And what switch 1 says? Switch 1 says, I am a root, there is no cost is 0. Okay, I think now it is clear that the spanning tree topology for RSTP with interface cost changes works perfectly and displays perfectly the conditions that we wanted. So currently we have our planet traffic, which goes from this switch like this, from this switch connected ports also like this, and from even this switch it also goes like this. So the mail server reachability has very high bandwidth. Only the traffic which is expected to go to the internet would go this way. So in this condition, when then the port on the switch 2 Ethernet 0/1 will become operational, it would become operational only if, let's say, Ethernet 0/3 will get broken or fail, then this port will switch back as a root port. If this one and this one, Ethernet 0/1, Ethernet 0/3 will fail, then the root port will become Ethernet 0/0 and will follow this path. Okay. This is all what I wanted to show you in this lesson. If you have any questions, you can ask them in the comment section of the video. See you on the next lesson. I highly recommend subscribing to my YouTube channel so that you don't miss any new lessons or setup guides that I release.